Thank you, Allison. Thanks, Dave, and thanks to all of you for coming today. As we said, we are talking about masonry details, prototypes, and notes from a structural perspective. I'm a licensed PE in Colorado. I grew up in Wisconsin, got my civil engineering degree from the University of Wisconsin-Platteville, then moved out to Colorado. Worked at a consulting engineering firm there for 11 years and then joined Force in 2013. And Force has been a consultant with the masonry industry back all the way to 2010. So I think you've seen the learning objectives. We're going to talk a little basics up front. I'll try and go kind of quickly through that since it's a little more of a review. We will talk about some general notes, what we want to see there, some common details of partition walls and other common masonry walls. And we'll talk about some masonry details, how and when to use them, some things to watch out for. So first, masonry is some of the parts. We got CMU, mortar, grout, reinforcing. The concrete masonry unit is a fundamental part of masonry construction. Because of that, strength of the block is a key component in the strength of the wall. And what we find in the Midwest is that very often we're getting blocks that are around 3,000 PSI or higher. So we're not just getting the minimum, even though even whatever we ask for, we're getting better than what the minimum is. Mortar is the glue that binds the CMU together. Not as strong as the CMU, but it doesn't need to be. We have the different types. Type S is normally what we use in structural applications. There are other types as well that we run into. Also a difference between mortar cement and masonry cement in that mortar cement has more tensile strength, and we often see that more in unreinforced applications. The grout is not the same as the mortar. Grout is used mostly to fill our masonry cores, especially when you have reinforcing, to get the reinforcing and the CMU to work together. And we can have fine or coarse grout or self-consolidating grout depending on what kind of obstructions or how much we have in the masonry cells that we need to work around in order to avoid having voids. The grout needs to be at least 2,000 PSI, and it does need to be greater than or equal to F'(m). So if we're calling out a higher assembly strength, we need to make sure we're calling out a higher grout strength as well. Reinforcing, the masonry construction is similar to reinforced concrete in that the concrete and the masonry are good in compression, not as good in tension, so we will add reinforcing to increase our strength, both due to axial tension or flexural tension. It's also going to help us prevent cracks. We need to be a number 9 bar or smaller, and then we have some more criteria that we have to look at as well. I understand these next couple of tables are a little out of date based on information from the 2022 code, but basically it just kind of illustrates that we need to think about what size block we're using if we start getting into larger bar sizes, and what actually fits in there without obstructing our cells too much. So something like this, I think, is not accurate, but to kind of shows that if you want to, especially if you want to put multiple bars in a cell, you have to pay attention to how big your block actually is and what's going to fit and be allowed by code. One of the interesting things, I learned most of my masonry information after I came to Force. So something like this I thought was pretty interesting. We surveyed a bunch of masons and said, what's your preference for reinforcing when you're doing masonry? So we gave them an 8-inch, hypothetical 8-inch wall and a 12-inch wall, and then 4 options for each. And as you look at these, the options are kind of similar between the two. So option A is a larger bar at a larger spacing. Option B is a smaller bar at a smaller spacing. Option C is 2 bars in each reinforced cell, and then option D is an alternating staggered placement. So at one cell, you're at the inside face, the next cell, you're at the outside face, and then on down the line. And what we saw was, this is for the 8-inch wall. The first choice preference was that actually grabbed the wrong thing there. That's supposed to be around the number 6 is at 48. That was the first choice there. The Masons preferred the larger bar with the larger spacing. You have fewer bars, you have fewer cells, you need to grout. That makes for a more efficient construction. What was their least favorite choice was the alternating staggered placement. For the 12-inch thick masonry, on this one, you can see that by a slim margin, they preferred the smaller bar at the smaller spacing. I think what happened was the number 7 started to feel a little too big and just harder to work with. So in that case, a small number of Masons preferred the smaller bar at the closer spacing. What was not close was that, again, their least favorite choice was the alternating staggered placement. And I think the Masons would just rather do the same thing in each cell and not have to worry about, now in this cell, where does the bar need to be? Which one did I do in the last cell? That kind of thing. Walls are defined by the code as a vertical element with length to thickness ratio greater than 3. And once we have more than 200 pounds of axial load, we are considered a load-bearing wall. We'll talk more about some walls further on in the presentation. Lintels are beams in masonry. It is common to have bottom bars in our masonry lintels. Kind of the standard way for designing masonry lintels was as a simply supported member, pinned at each end. So all our flexural tension is on the bottom. So we have bottom bars. Now with finite element design that we are seeing more and more, that is getting us a more efficient lintel design, but it's also giving us some fixity at the ends, which puts some tension into the top. So we are seeing more and more lintel designs with top bars. It is possible to put shear steel in masonry lintels, but our preference generally is to make the lintel deeper and resist the shear with the masonry if we can. So add additional depth when we can, but if we need to, we can add shear steel. Column is a structural member not built integrally with the wall. So you can see our member at the front of the little canopy there is a column. The one at the back, which would be built integrally with that wall, would not be a column. We could just design that as another piece of the wall between the opening and the control joint. Now, if we have a steel lintel on that opening, we're very close to our control joint there. We are about to cut that off from the wall above, so we may be defined as a column at that point and then trigger all the code provisions that go along with that, and possibly even a cantilevered column. So just some more of the things, kind of the things we like to talk about are lintels. We like masonry rather than steel lintels, and then control joint placement we need to pay attention to as well. So some of those code provisions on the columns, they need to be reinforced with between a 1/4% and 4% of steel in a minimum of 4 bars, and then lateral ties that are at least a 1/4 inch in diameter. The code does allow for lightly loaded columns, which are columns that have no more than 2 kips of axial load and are no taller than 12 feet, and then also in low seismic zones. And at that point, we can reinforce them with just one number 4 bar, and there's no tie requirement. The next part of the presentation, we'll move on to talking about the notes now. We'll talk about the material notes as far as they apply to the design criteria, and then the general notes as well. So for the general notes, we'd like to not try and define the reinforcing in the notes. Same with control joint locations. and we don't want to define lap splice lengths in the notes either. This is kind of things for more typical projects, larger buildings. If you have a little small thing like a sign foundation or a little small outbuilding or something, maybe this is okay to do since you're not going to have a lot of different stuff going on. But in general, we like to avoid kind of these catch-all statements in our general notes. So for the material notes, we prefer to not just call out the assembly strength, the F prime M. We like to call it the assembly strength, the CMU, block strength, the grout, and the mortar type. So an example as we see here, we would show we want our F prime M to be 2,500 PSI, and for that, based on the unit strength method, we show that our block strength should be 3250 or greater. Grout strength, since the F prime M can't be higher than the grout strength, grout should be 2,500 or greater. And then call out a mortar type S, which is typical for structural applications. It is possible to have two different F prime M's on the same project. I don't know how common it is, but I think we've all seen projects with different concrete strengths on the same project. So maybe, for example, if we had a project where our masonry shear walls are our lateral system, we might need a higher F prime M there. And then if we had a lot of masonry partition walls, we could just go with a more typical F prime M value for those and make more efficient use of our materials. I mentioned the unit strength method. This is the unit strength table from the TMS code. You can see that center column there dealing with type M or type S mortar. You go down to the entry that says 3,250 PSI. And then on the left-hand side, that gives us an F prime M of 2,500. So that is what I was basing the previous example off of. I mentioned that in the Midwest, a lot of the block strengths are higher than the minimum. We've been surveying block producers around the country for a few years. A lot of this info is a bit dated. We're working on updating that right now, but you can see on this screenshot that we have, we're looking at 8-inch normal weight block. We had gotten 43 different test reports from producers around the country and found that of those reports, the minimum block strength that we saw was 3,000 PSI. And the average out of all those reports was 4,400. So the 4,400, if you remember back to the table on the previous slide, that's getting really close to getting us an F prime M of 3,000 PSI. So even the minimum is significantly higher than the 2,000 PSI that the minimum that the code allows. So what we like to recommend is early on in a project, if you know it's going to have masonry, talk to block producers who are local to the project, see what kind of block strength they are regularly producing, and then base your designs off of that. The other option for F prime M is the prism strength method or prism test method. Basically, you build 3 prisms using the materials you're going to have on the project, and then after 28 days, break those prisms. Take the average, and the strength of those is the F prime M for the system. So as an example, we have our 3 prisms. These numbers might be a little high for some of, for kind of an average project, but in this case, the average that we got from these 3 is over 4,000 PSI, and in this case, that would be our F prime M. Obviously, the drawback with the prism test method is that you need to wait the 28 days to break these and test them. But if it gets you a much higher F prime M, maybe that's worth it if you can get that in the schedule. And of course, F prime M is so important because everything with masonry has to do with that. All the strengths of our walls, lintels, columns, but lap lengths get shorter. and connections to masonry are more efficient as well, whether we're talking cast-in-place connections or post-installed. So with general notes, as I mentioned, we want to try and avoid making general catch-all statements. So for example, don't try and define maximum reinforcing spacing in the general notes. Depending on what kind of masonry we have on our project, unreinforced walls could be a reasonable option, and a note like this might eliminate that possibility. And a lot of times, I remember in my previous job, I'd see a note that says maximum reinforcing spacing is 48 inches. If you're in a low seismic zone, you are not going to need bar that close together. So it's going to add unnecessary reinforcing possibly. We also don't need to add a top of wall bond beam to every single wall. There are obviously walls that will require that, but a note like this could arbitrarily add an unnecessary element on walls where it's not required. Control joints are another thing that we'd rather not try and define in the notes, especially if we're not distinguishing between joints in the veneer versus joints in the concrete masonry. They have different requirements. The brick is going to expand, the concrete masonry will contract. The brick is not reinforced, the concrete masonry often is. So there's different requirements for the two. And what we find is that it's better to show specifically on plan or specifically on the drawings where we want our reinforcing. So in the structural CMU backup, typically we'd see joints on the structural plans. On the brick, or for the brick veneer, we typically see those on the architectural elevations. It can just lead to too many problems if we try and define it with words, especially when we're talking about opening locations or beam-bearing locations. A general note leaves it up to somebody else's interpretation where the joint is going to end up. So we have control joints to allow for minimum horizontal reinforcing. Unlike concrete, masonry does not need horizontal reinforcing to be bars. It can be wire gauge or wire reinforcing instead. And those in combination with the control joints will keep us from getting cracking where we don't want it if it's done correctly. NCMA recommends that with minimum reinforcing, our control joint spacing is a maximum of 25 feet or 1.5 times the wall height, whichever is smaller. The other option for controlling cracking is to add more horizontal reinforcing. And as we get to 0.002 times the area of our wall, we can actually eliminate control joints altogether, as that amount of reinforcing will keep the cracking small enough that it's not going to be noticeable. One thing to notice in this table from NCMA is that since this requirement is based on the wall area, we need a lot more reinforcing once we go from a partially grouted wall to a solid grouted wall. So that's something to keep in mind. If a solid grouted wall might be something that's required, is that in order to eliminate control joints, you'll need a lot more bond beams at that point. With lap splices, the next thing that we'd prefer not to try and define in the general notes. A lot of different things can change the length of a lap. Bigger bar means a bigger lap length. Our reinforcing location in the cell will affect it due to the bar cover, whether we're in the center or at each face. The bar spacing can affect that as well. And then of course the F'(M) also has an effect on that. So for that, especially if we get to projects with some different conditions in it, we would prefer to include this information in the wall schedule. This is just a sample wall schedule that shows some of the differences. Wall 2 has a bigger bar than wall 1, so we have a larger lap length. Wall 3 has the same bar size, but now we're at the face of the cell, so we have less bar cover. That increases our lap length. Wall 4 is the same as wall 2, except now our F prime M is higher, so we have less of a lap length there. And then wall 5 is again the same as wall 2, but now we have a 12-inch block instead of 8-inch. So with the bar at the center, that increases our bar cover, and our lap length goes down again. We may not have every project with a complicated wall schedule like this, but if we do, we can make some efficiencies by checking the lap length for each situation. So next we will move into some prototypes, and we'll talk specifically about some different types of walls that we see a lot in masonry construction. Shear wall is a wall that is part of the lateral system. It resists in-plane shear loads. And in seismic regions, we need to clarify our walls as ordinary or detailed plane walls, or ordinary, intermediate, or special reinforced shear walls. And some of those requirements for each are shown here from the TMS code. You can see the requirements for our ordinary walls. Bar size is at least a number 4 vertical, 120 inches max. We need them near the edges of our openings and at the ends of our walls and at joints. It explains our horizontal reinforcing requirement. You can see that reinforcing is required within the 16 inches of the top of walls. So for that, we would not need a bond beam in that top course. It could be one below that. And this is based on ASD or strength design. Intermediate reinforced walls have all the requirements of ordinary walls plus a few more. The big one being that now our maximum vertical reinforcing spacing is 48 inches. With special reinforced walls, again, all the requirements below, all reinforcing, so vertical and horizontal, now spaced at 48 inches, and many other requirements as well. This is just kind of a summary, so you'll find all these requirements in the TMS. Next, we'll talk about partition walls, and partition walls are interior walls with no structural function. So since we're interior, we don't have any external wind pressures. We have, it's not a load-bearing wall, no axial load, and not part of the lateral system, so no in-plane shear walls. Chapter 7 was added in the 2013 code, and in that chapter, it makes it clear that we need to take care how we connect these walls so that we're not getting loads that we did not account for, which are finding their way into the walls. So we've seen, definitely seen some complications in our partition walls, maybe because of these catch-all notes in general notes. So we like to try to simplify them. Again, these are partition walls. They're not part of the lateral system, so let's get rid of unnecessary horizontal reinforcing, which we can do in lower seismic zones. We may not need a top-of-wall bond beam, so if we can eliminate that, that's helpful. And then minimize the vertical reinforcing as well. Again, as long as we're in a lower seismic design category, we don't need our vertical reinforcing in our partition walls at 48 inches on center. And think about the top and bottom connections as well, and are those something we can simplify? Here's a detail for a partition wall. In this case, we have a continuous angle at the top of the wall, and there is no hard connection between the vertical leg of that angle and the masonry wall. And there's a gap at the top of the wall, so that allows the structure above to deflect without putting axial load into our partition wall. And the wall can also move independently in plane as well. But this angle does provide the pinned top support that we are most often going to have with our partition walls. It is possible to do a cantilevered partition wall. In this case, we have a compressible material at the top that still allows for that vertical deflection of the floor above. This may be something we would see where the partition wall is exposed to view, and we don't want to have to see that angle or whatever top connection we might have there. So this is good for aesthetics, but we have to think about now we need to add reinforcing because we need to fix the base of that wall and add reinforcing to the wall as well because we are no longer simply supported. Along those lines, there are partition top anchors, which are proprietary partition anchoring systems, which are concealed and not visual, and they provide that pinned out of plane support at the top of the wall, but they allow for vertical movement and in plane movement. So it would get us the type of connection that we would need for a pin connection at the top of a partition wall. And these are proprietary systems that you can get from different producers. Here is kind of an example of what kind of reinforcing we need for partition walls. In this example, we're using an F'(M) of 2,500 psi. The only load we have is our IBC minimum out of plane load, which is 5 PSF for service, 8 PSF for ultimate. And this is looking at pin support at the top and bottom of the wall, and we are in seismic design category A or B. And what we see is that there are a lot of combinations here of block size and wall height where we don't need any reinforcing at all. Again, this wall is not taking any structural loads. So with an 8-inch block, even up to 18 feet, for our partitions, we don't need any reinforcing, again, provided we're in a low seismic area and we have that pin support at the top. If we were in seismic design category C, the code no longer allows unreinforced masonry. So all the cells on the previous slide that said none now just changed to number 4s at 120. So that's still very little reinforcing that is required. And you can get the idea that if we had a project with a lot of masonry partition walls where maybe there was a note that said maximum reinforcing spacing is 48 inches on center, we'd end up with quite a bit more reinforcing than we would need in this area. In seismic design category D, the maximum reinforcing spacing is now 48 inches, so we kind of start losing our advantage here on the reinforcing spacing. And then in E or F, we have that same vertical reinforcing spacing, and now for the requirements on grouting and horizontal reinforcing spacing as well. But in those first couple of slides, in the low seismic areas, we can really achieve some economy by looking at what reinforcing we have in our partition walls. On the Force Consulting website, we've done a few different technical papers about masonry design and masonry construction that we call Masonry Insights. We have one there on partition walls. It's one other option for just an information resource as you are going through design on a masonry project. We also checked a similar condition with an exterior non-load bearing wall. So we're not a partition wall anymore because now we have to resist external wind pressures. So depending on how high those pressures are, we may not be able to simplify these as much as we did our partition walls, but it was interesting, I think, for me also to see what we ended up with here. So this is a standard masonry wall, not an infill wall. It's not in the plane of the structure. The same F'(M) of 2,500 psi. We based these components and cladding loads on a 60-foot tall building in Chicago. We assumed pins at the top and bottom again, and we also assumed that wind loads are going to control our design over seismic. And even with this external wind pressure, an 8-inch block, maybe 16 feet might be something you'd see at the bottom level of a building with a higher floor-to-floor at the first level. It's still 5s at 64, so we can still space those bars out quite a bit more than I know I was used to doing when I first started my career. And you can see in some of these other situations as well what kind of reinforcing spacing we could get in some of these situations. Similar to those partition top anchors that I showed a couple of slides ago, these same companies do make anchors for external applications, larger rod diameters, a larger head diameter on these connectors. So things like this are still an option to use for out of plane or external walls that get the larger out of plane loads and still achieve a pin connection at the top that is not visible. So now we will go into some of the detailing. The first thing that we like to mention is how control joint location affects our design. We have an entire presentation that just deals with control joint location, so we get into a lot more detail in that than we do here. But some of the things I'll mention is that it's going to affect both our in-plane and out-of-plane behavior. As far as out-of-plane goes, control joint location is going to affect our lintel design. We like to recommend to have control joints at least 2 feet away from our opening. That can change depending on how big your opening is, but that's a good rule of thumb to start with. And that affects whether we can take arching action into account in our lintel design or not. Can also affect our pilaster design as well. If we end up with a joint in the middle of a pilaster, obviously we're not going to have the same capacity that we originally thought we were going to when we designed. And as far as in-plane design, the same overall length of wall divided into a fewer number of longer panels is going to give us a better in-plane performance than it would if we had more joints with more panels that are not as long. I mentioned arching action. That with lintel design is basically where we say that with the masonry lintel here, the only load that lintel sees comes from inside this 45-degree triangle. So in this case, it's just the self-weight of the wall there. Any load from outside of that triangle, the self-weight of the wall, structural members bearing on it, that all basically flows around the opening and never touches that lintel. So because of the horizontal component of that load, you're going to get some thrust force in the wall at the ends of this lintel. And if you don't have enough masonry between your edge of your opening and your control joint, there won't be enough masonry there to resist that thrust force. So at that point, you'd end up designing the lintel for basically all of the load that sits on top of it. So for that reason, that's why we like to have as much space as we can between the edge of our openings and our control joints. So control joints, as I mentioned, they're there to panelize the wall and give us better thermal performance in conjunction with minimum horizontal reinforcing. That's going to, we know we're going to get cracks, so if we do this right, they're going to happen at the control joints and not be an aesthetic issue like they would if they were cracking through a block. This is kind of a typical control joint using just the typical masonry blocks. There are also kind of a more special application as well. You get a better thermal performance with this setup, but you do need special blocks. One other issue with detailing that we run into sometimes is when we have a large point load acting on our masonry wall, and engineers at that point have to figure out how am I going to resist that load. One of the options we see people go to sometimes is to put a steel column that fits inside the masonry core. So obviously you're limited on what size steel you can fit in there. Usually we're thinking about a square HSS member at that point. So not only are we limited on size, but a lot of times we run into issues with constructability as far as what is there first, and do we need to cut and grind blocks to get those steel sections to fit? So there's other architectural considerations as well when we're adding steel into our masonry. So ideally, I think we would rather see the load resisted by the masonry itself. So let's have a pilaster in our masonry. If we can resist the load within the width of the wall, that's probably the best case scenario. We have nothing visual changes here. Everything's inside the wall. We're not affecting any square footage calcs if we, to bring the pilaster inside the building. So no issues there. One note that we do have on here is over that pilaster width, we can't have control joints in that location. So that's something where we could run into an issue if all we had for locating control joints was a note, especially if the pilaster is all inside the wall. Somebody may not quite realize that what's going on there, and might negatively impact our pilaster capacity. If we need more capacity, we can add width to our wall to resist that axial load. I think everybody's used to seeing pilasters like this in concrete construction. We can do it in masonry as well, and gain significant additional vertical capacity by adding width to our wall. There are special pilaster blocks as well. These make it a lot easier to install our vertical reinforcing and also our lateral ties. So if something like this works and we can get blocks like this, these might be pretty efficient for masonry pilasters. When we talk about adding steel, obviously we can run into issues. This one, the HSS kind of looks like it was maybe a little too big for the cell area anyway. But with the steel column being installed first, the masons had to break out the face shells, and also there were coordination issues with the anchor bolts as well. So not just to install the blocks and get them around the HSS column, but also to get them to fit around the anchor bolts. We had to make some modifications to our masonry wall there. So hopefully that's not an application that would end up being visual in the final condition. Here's another situation where maybe both the masonry and the steel were installed within tolerance, but maybe in opposite directions. So in that case, we had to shave down the face shell on the masonry to get that to fit around our HSS column. So we're building with masonry, so it's best to do all our structural work with masonry instead of trying to add another material into it. We tend to run into a similar issue with lintels as well. Do we want to do our lintels with steel or with masonry? Masonry lintels are built integrally with the masonry wall. Obviously, that's the same material. So it is an integrated element of the wall as opposed to steel, which is a foreign or isolated element. It's a new material with different properties, which can lead to issues. And again, our architectural considerations, again, for putting steel into our masonry wall. So with masonry lintels, construction can be pretty quick and economical. You have the same people who are building the wall are going to place your lintel as well. For thermal movement, it moves at the same rate as the wall. You don't have two different materials with different thermal coefficients. Masonry lintels can be built in place or prefabricated. The prefabrication would help the shoring issue that a lot of contractors don't like. Masonry lintels are pretty easy, up to 15 or 16 feet. depending on how much wall we have above the opening, so how deep our lintel can be. But we can do longer spans as well. One example we had, I believe it was in a performing arts center. Our lintel, or our opening, was 52 feet long. And this is obviously not an everyday occurrence because it was 12 courses high. I believe it was 2 wides of 16-inch block, and it still had shear reinforcing in it. So not something you're going to see every day, but you don't have to go to a steel lintel just because the opening is long if your conditions will allow it. I mentioned prefabricated lintels. This one is 12 feet long, build it on site, and then as it sets up, lift it in place, set it with a crane. Another thing to think of when we're talking about steel lintels versus masonry is the jambs. This is a detail for a jamb with a masonry lintel. The steel for our jambs needs to be full height, needs to go from the floor to the roof or the diaphragm above without being interrupted, which is not an issue when we have masonry lintels. Again, no control joints located within the jamb width. For a jamb with a steel lintel, that steel is going to need a bearing length on each end, and that would interrupt any jamb steel there. So we need to make sure that, as you can see here, we have our jamb width and our total width, the total width accounting for the steel lintel bearing, to ensure that we still have jamb steel that can be full height. So for steel lintels, scheduling can become an issue. We have a different trade now coming in to put in our lintel. If we're in an exterior location, that steel lintel might need corrosion protection. They often need bearing plates, and we can run into issues with bearing plate thickness if that's thicker than the joints in the masonry. And it can be a thermal bridging issue as well. So as I mentioned, steel lintels are used to solve the shoring issue, but they do add more complications that we need to take into account. And as people who are here working on talking about masonry, talking about the advantages of masonry, if we're building a masonry wall, we would just rather see a masonry lintel. So here's kind of a cutaway view showing a little bit of the jamb steel issue that I was talking about. You can see how the jamb steel in that cell adjacent to the opening can run right through there and run full height continuous. Whereas with the steel lintel, we have to move that reinforcing back to avoid the steel lintel bearing. And you also see now anchor bolts and hairpins, maybe a bearing plate that's not shown there. So just we get more things going on here. So I think the one more thing I wanted to go over was just some kind of standard roof details that we run into a lot. This is like a standard roof joist bearing on a masonry wall. The note here says we'd like it to bear at coursing. That's great if that can work out, but obviously that's not going to happen all the time, especially if you're talking about a roof with roof slopes, that kind of thing. One thing we do like to mention is to have that bearing plate away from the edge of the face of the masonry if we can, for a couple of reasons. First is that by pulling that back, we're going to apply that end reaction closer to the center of our wall. We're going to get less out of plane bending due to that eccentric reaction at that point. And also, with the bearing calculation for bearing on masonry, if you're familiar with it, it has the A1, which is the area of the bearing plate, and then A2, which is the confined area. So if you're away from the face of the wall, your A2 grows larger, and sometimes you can achieve a larger bearing capacity with even a smaller plate just by giving yourself some confinement there. One other thing that we like to specify is don't directly connect each end of your roof member until the building's enclosed. A hard connection on each end while still exposed to the sun and the elements can add some push and pull on that member that we don't want in our masonry. Similar situation with a roof beam instead of a joist. It's kind of the same deal. I didn't mention it with the joist, but it applies there too. We want to grout that pocket solid after we install for fire protection. Again, minimize the bearing plate size by moving that away from the edge of the masonry as we can. And also consider the stud length on our bearing plates. If you're using a bond beam block that has the U blocks, keep that in mind if it's going to conflict with our studs on our base plates. One of our other presentations has a picture of a contractor with the U block and then the bearing plate that was called out, and there's like a couple inch gap between the bottom of the plate and the masonry surface due to how long the headed anchor studs were. Same note again, do not directly connect the beams on each end until we enclose the building to mitigate effects from beam expansion and contraction. At the non-bearing side, so the wall that's parallel to the roof framing, we're attaching a roof deck, which is going to be a much lighter load. If it's light enough, we don't need a bond beam there for the connection. We may need it for other reasons, but we can connect hollow anchors into hollow cells if you change the anchor that you have. So it looks like I've done okay on timing here. In conclusion, we talked about how and why we specify each element of masonry. We talked about trying to avoid catch-all comments. I was reading through this earlier thinking that I made a general statement to say we want to avoid general statements, but I think it still works. And then we talked about structural details. We talked about the standards that we have, know how and why we use them, when they apply, and then be aware of the limitations of different details. Watch out for common typical masonry detailing errors or things that we may not think about when adding steel or doing other things that might be kind of typical in masonry construction. Some of the resources, obviously the building codes, but check out the BIA Tech Notes on the website for the Brick Institute of America. Also the NCMA Tech Guides on their website. Lots of great information there. International Masonry Institute has good information on their website. And then we do have some technical papers on the Force website as well that are hopefully helpful during design. So with that,